to the cloud is what I want. All right, guys. So today we'll talk about feeds, feed types, importance of feed processing, mainly going to focus on grains and conserved forages, and then some byproduct feeds. Okay. Okay. So I want you guys to be able to identify the different components of corn grain. There's really four parts of that corn kernel. Okay. So know why we process grains. Okay. Understand how we commonly process grains and be able to rank them in terms of their impact on, so which processing method is going to have the biggest increase in available energy, starch digestibility, dry matter digestibility. Okay. Know common corn milling byproducts and from what co-product production they're from. Okay. Know how different post-processing of these byproducts can be a benefit or a detriment to those ingredients. Okay. Big example is drying distillers grains. Okay, that's going to have a big impact on the digestibility of some of those nutrients. Okay. Be able to describe why we include roughages in a total mixed ration and understand roughage processing and how it can impact that TMR and the response from that animal. Okay, so grain processing. So it is do that because we want to break the pericarp, okay, and expose the endosperm. Okay, that pericarp is very fibrous, has a lot of structural fiber that microbes can't attach to. So if we don't break and expose that endosperm by breaking that pericarp, and the microbes can't get access to the starch. Okay. Okay. So we process grains because we want to increase starch availability by damaging the pericarp. So the pericarp is undigestible to microbes. Feeding whole grains. So if we unfeed a grain that's unprocessed, the only way microbes will get access to that endosperm is if they masticate and chew that pericarp, okay, to expose the endosperm. So if we think about grain, and let's say an animal, just imagine an animal is take a big mouthful of grain, there's going to be a large proportion of those grains that won't be masticated. They will be swallowed whole, okay? And if it gets swallowed whole, chances are it's not going to be regurgitated back for rumination. There's going to be a large amount of grain that is unavailable to the microbes. Okay? So the endosperm, starch containing, it represents about 80% of the kernel. Okay? Pericarp, fibrous, mostly indigestible. It's the outer covering, the kind of defensive layer that the corn produces to protect the germ. Okay? So the germ is really the only living part of the plant. So if we were to plant this seed, the germ is where that plant would sprout from. Okay? So if we plant a seed, okay, that germ starts to sprout, it is going to draw energy from that endosperm to produce the plant until it gets enough leaf matter above ground to start photosynthesizing. Okay? The tip cap, so that is where the kernel attaches to the cob, where nutrients flow from the plant through the cob into the grain. Okay? So it's also very highly fibrous. And so like the bran is the pericarp and the germ. So sweet bran, which is a corn gluten feed, which really corn bran is composed of the pericarp and the tip cap. Okay. And that's a byproduct of what? Um, but for a specific purpose. Yeah. Corn syrup production. So corn gluten feed is a byproduct of corn syrup production. Distillers grains are a byproduct of what? Ethanol, right? Okay. Okay. So this was an interesting paper by Karen Buchman out of Canada. She's kind of a famous ruminant nutritionist, recently retired, but she investigated the effects of mastication on fermentation characteristics of the whole grain. Okay. They did total feces collection, and then they isolated the grain components of that feces. Okay. When fed whole, 75% of barley was excreted whole. Okay. That should make sense because it's a very small grain with a relatively hard pericarp. Okay. 49.5% of corn was unmasticated. So they were able to more effectively masticate corn. Again, that makes sense. It's a larger grain compared to these uh, barley and wheat. And 82.4% of wheat was actually masticated, or excuse me, excreted as whole. Okay. So larger grains are more likely to be damaged through mastication if they're fed whole than smaller grains. Okay. They also looked at an in-sacco digestion. Who knows what that is? You guys did it in Feeds and Feeding. Sacco sounds a lot like sack. So what would that be? Yeah, we put it in that mesh bag, and then you put it in the rumen of the animal and measure ruminal disappearance, right? Ruminal digestibility. Okay. So they looked at dry matter disappearance of barley, corn, wheat. They either cut that grain into quarters, halved it, fed it to the animals, and collected chewed pieces of grain, or put it in the bags whole. So if you put any of these grains in whole, very little of it will be digested. The more you process it, the more likely that grain will be digested. Okay. So this is incubation time. This is kind of a typical dry matter disappearance curve from these in situ digestions. Okay. So you have a period of time where they have a rapid increase in disappearance, right, or digestibility, and then it kind of plateaus over time. Okay. Does that make sense? Okay. So processing grains is very important. Can't really feed them whole because if they do, a large proportion of it will be excreted in the feces whole and undamaged. Okay. So ways that we can process grain. Probably the easiest way is to dry roll it. Okay. We would put the whole grain through these mills. They have rollers in there that as that grain passes through that roller, it'll literally crack. So dry rolling, you could also hear it as crack. It's like cracked corn. Okay. We'll see if YouTube wants to, what advertisement YouTube wants to show us today. Oh, American Airlines. That's typically it.
It's being dumped into the auger, which is augering it into the roller, and then the roller is gonna roll it, so crush it, so it's more available to the cows. Once the corn has been rolled, it's then dumped into another auger and augered into our bin where it'll be stored all winter, and that's where we'll get the corn to dump in the mixer to feed the cows.
So whole corn, cracked, dry rolled corn. Okay. That machine's costs money, right? But it's going to be a lot cheaper than some of the other processing methods. Okay. Okay. High moisture corn. So whenever I say high moisture corn, where are we thinking? What location in the US is going to feed high moisture corn? Midwest. Can't really transport high moisture corn because you'd be paying to transport a lot of water. Okay. So when we import grain from the Midwest into the high plains, it's all going to be dry, and the standard dry temp or percent of whole corn is 84.5%. So high moisture grain, they will harvest this grain when it's at a 28 to 34% moisture, so that's 66 to 72% dry matter, okay? So just said that most of that's going to be put up in the Midwest, but here we have Scott City, Kansas, which is southwest Kansas. So truck goes, combine dumps corn from field into truck. Truck comes, dumps corn out here. They're going to put it into a roller mill, very similar to dry rolling. That roller mill is going to blow out rolled, cracked, high moisture corn. Then they're going to use a tractor with basically a, what do they call it, blade attachment on the front to push that rolled, that processed high moisture corn into a pile that they'll then cover with plastic and store it as silage. Okay. I don't know how I would handle being the guy driving the tractor on those pits. He's a nice looking guy. So they're driving it up, they're pushing it up to mound it, but also as they're driving over it, it's compacting to get rid of some of that air.
Now we got somewhere around 750,000 bushels.
750,000 bushels. So you multiply that by 56, and I'll tell you how many pounds of corn they're putting up. So putting up 1.5 million bushel of corn. And so they'll open that silage pit and pull through it throughout the year. So why would we want to ensile high moisture corn? I think the answer is pretty obvious. Anybody know? What would happen to that corn if we just left it out in the open? Sure, mold, spoil, right? So when we put it in the silage pit and they're packing it to try to preclude oxygen, what's going to happen? Guys, remember from feeds talking about silage? Fermentation, what's that going to do? Decrease the pH. So when it decreases pH, what's going to happen? This is in the silage pit.
Oh, in the silage.
Yeah. So decrease pH in the silage pit, eventually gets to 4 at a pH of around 4. There'll be no more fermentation. Okay, no more bacteria can grow because the pH is so low. So it's going to preserve that grain. Okay, does that make sense? Okay, takes about 60 days-ish, if I remember right, to get to where that pH drops low enough to where it's preserved. Yeah, it'll be more digestible than dry rolled. Okay. So the input requirements for this, right? You still have money, you have equipment, right? Takes a lot of time, okay? But it's going to be much less than how we process corn in the high plains, right? So steam flaking, okay? Steam flaking can be done at different, what's called bulk densities, okay? So I guess let's describe what that is. They put the corn into these steam chests, and then they steep that corn in steam for a period of time. There's no set amount of time. Different feed mills may do different things. I think it's typically around 30 minutes to an hour or so, unless I say differently here, which I don't. Okay. All right. After its steeping time, it'll roll out or be put out at the bottom of the steam chest into another roller mill. Okay. So that steam is going to reconstitute that grain. So it's going to make it higher moisture. Okay. Then whenever it comes out of that steam chest, it's going to be rolled flat into a flake. Okay. So we can flake that to different bulk densities, okay, which we call flake weights. We do that by adjusting the roller. So we can adjust this using this roller pressure arm to bring the roller closer or push it farther back to adjust the roller gap to determine how thin that grain will be processed. Okay. Okay. Typically, we're doing somewhere around 26 to 28 bushel or pounds per bushel. Okay. We talked about this previously, but a lighter flake weight, a less dense flake will have more starch availability than a more dense flake. Okay. By being further processed and being flattened out, it's going to decrease that grain's bulk density. Okay. So this study, SMOC 2021, compared a 26 to 33 pound flake weight. So the differences in processing didn't really impact total amount of starch available in the grain. Wouldn't expect it to, okay? But the enzymatic starch availability, but the availability of that starch almost doubled, okay? So lighter flake weight means more starch availability, okay? Fed that to animals, okay? Didn't really see any difference in average daily gain, but by feeding a more starch available grain, reduced dry matter intake, so that a lighter flake had better feed efficiency. Okay. However, because that starch is more available, okay, more propionate production, more starch fermentation in the rumen, driving ruminal pH down. Ruminal pH causes ruminal acidosis. Okay. Ruminal acidosis causes lesions in the rumen wall, allows bacteria to translocate from the rumen into the bloodstream. That bacteria then gets transported to the liver and causes liver abscesses. So by feeding a lighter flake, you increase the incidence of liver abscesses. Okay? We'll talk a lot more about that tomorrow, or Thursday. Not tomorrow. You guys wouldn't be here. Okay? Okay, I took this at the feed mill at Wrangler Feed Yards. They're, what is that, by Tulia? Somewhere in the Panhandle. Okay. Steam chest, roller mill. So they'll steep the grain in the steam chest. It dispenses it into the roller mill, and then they'll take that grain out. And pretty much you're going to be creating the flake for that day. Okay, so most of that flake that you're making that day will be fed that day. Okay, so they'll come in and fire this thing up prior to morning feeding. Okay, this is a picture of an old roller that's in this thing. Weighs a whole lot. I don't even remember what it weighs, but it's about 2.5 feet in diameter. Okay, and then they have these grooves in it. Okay, so those grooves, when they get worn out, you can actually have a machinist come in and resharpen them. But eventually, you have to get a new roller. Okay. Okay. John Matsushima, uh, famous, very famous ruminant nutritionist from Colorado State, worked at Nebraska for a while, but he is the inventor of steam flaking. He also invented the feed truck and did some of the first studies with implants. Okay. It's kind of a hero of mine. Okay. Born in Denver to Japanese immigrants. okay, came up with the idea for steam flaking while he was in a hotel room eating cereal. Like, why don't we make a hot breakfast for our cattle on feed? Okay. Um, okay. Conducted verse studies with implants, ionophores, and distillers grains. So, kind of a interesting story. He just recently published a book, which I have. Don't know if I'll have time to read it, but okay. So, according to the NASM, so that's the Beef Cattle Nutrient Requirements book, okay, they have a feed library. Uh, Pulled out the data for steam flake corn, high moisture corn, and dry rolled corn, okay? Uh, High moisture corn put up a lot wetter than typical traditional corn, so it's going to have the lowest dry matter. However, the process of steam flaking adds moisture to that grain, okay? That's actually, in a lot of years, the number one way feedlots will make money. They will buy grain, steam flake it, add moisture, and then sell it to their consumers at about the same price that they purchased it. So in essence, they're selling some water, okay? So that's one way they can add feed markup, okay? Don't really see an impact on crude protein. However, ruminal degradable protein as a percent of crude protein is lowest for steam flake corn. Why might that be? So it's decreasing, steam flaking is decreasing ruminal availability of protein in corn. Why could that be? What happens when I add heat to bread? Not necessarily breaking them down, but you're causing bonds from protein to fiber, okay? So that's called the Maillard reaction, okay? We'll talk about that in the context of distillers grains in just a little bit, but that heat causes Maillard reaction, forms Amendouri products, reduces the availability, the ruminal availability of that crude protein, okay? So dry rolled corn, in terms of relative to the other processing methods, will have the lowest TDN, okay, driven by a lower ruminal starch availability, okay. High moisture corn is more, and then steam flake corn is the highest, okay. So steam flake corn, steam flaking has the highest amount of starch availability, okay. So does that make sense why we will put the capital investment in the high plains to get the most out of that grain when we're importing 80% of the grain we feed? Okay? A steam chest is going to cost somewhere around $1 million. Okay? So we need to maximize our output of that corn because we're importing it all. And we have a much higher basis relative to the corn belt. So every time that train that's hauling that corn goes from the Midwest to the high plains, it is passing other bidders, right? And the farther out they get, the higher that price. Okay? So TDN, NEM, NEG, those are all going to follow each other. See no real impact on fiber content of these different processing methods. Okay? So steam flaking increases NEM by about 10% and NEG by about 12% relative to dry rolled. Okay? High moisture increases NEM by about 4% and NEG by about 5% over dry rolled. Okay? So this is why in the Midwest, where they're growing their own corn, one, they don't have to transport water by importing the grain, right? But two, they can get a little bit more energy out of that grain that they're growing on house as opposed to just dry rolling it. So it pays to have that capital investment in the silage pit. However, it doesn't make sense, the difference in energy gained between high moisture to steam flaking is 6 megacals of NEM per hundredweight. So that's like 5% increase or whatever. So it doesn't necessarily make sense to make that capital investment into a steam chest. Okay? Everybody follow? Cool. sorghum. All right, bye. You're good. Okay, this is sorghum, dry rolled, high moisture, steam flaked again. Okay, dry matter percent follows a similar pattern as corn. They did not have RDP values for high moisture and steam flaked in the tabular values. However, don't see much difference between dry rolled and high moisture. Okay, but you see a big increase between these other grain processing methods and steam flaked. Okay, so the percent increase in energy availability going from dry rolled to steam flaked is actually much greater for sorghum than it is for corn. So the value of steam flaking that sorghum is a lot bigger than corn. Okay, that is because sorghum has a very hard pericarp. Okay, so it requires, you can't often, and it's small berries, and there's a lot of variation between those berries in size. So it'd be very hard to take sorghum, run it through a dry roller, and get a uniform crack on that sorghum is one thing. Okay. Then the starch contained within sorghum also responds better and becomes more available from heat associated with the steam flaking. Okay. So just running it through a dry roller or even a roller mill prior to being ensiled is oftentimes not adequate enough to fully expose that endosperm component of the grain because of that really hard pericarp and the variation in berry size. Okay. All right, this data is from Owens and others, 1997, and it pretty much aligns well with the NASM tabular values. Okay. So they looked at 605 different diet type comparisons. So this was kind of a meta-analysis approach. Steam flaking improved feed to gain relative to dry rolled corn by 10.7% for corn and 15% for sorghum. So again, that benefit of going from a dry rolled to a steam flaked is greater when you're processing sorghum than when you're processing corn. Okay. Steam flaked improved ME, so metabolizable energy, relative to dry rolled by 15% for corn and 20.5% for sorghum. Okay. And I've already said this, but okay, as you go from dry rolled to high moisture to steam flaked, you kind of see dry matter intake decreasing. Okay, why would processing grain reduce dry matter intake? Think back to Meninsen and its impact on when we're feeding it to finishing cattle. What's regulating intake in finishing cattle? Oh, guys, I'm disappointed. Huh? Blood glucose, some kind of chemostatic signaling, right? Could be glucose, could be propionate, could be liver hepatic oxidation. Okay? But it's some kind of chemostatic signaling so that by increasing starch availability, they achieve that threshold at a lower dry matter intake. Okay? Does that make sense? Just like we saw with Meninsen when we're feeding it to feedlot cattle, you don't see any change in average daily gain, but you're going to decrease intake a little bit. So by holding average daily gain steady, decreasing intake, we're going to improve our feed conversion. Okay? So that's a very similar but much larger impact by grain processing than what the impact that Meninsen has. Okay? It's going to increase starch availability in the rumen. Increased starch availability in the rumen yields more propionate production. More propionate production will achieve that level of satiety, that chemostatic regulation of intake in these finishing cattle. Okay, so they reach satiety at lower thresholds. Does that make sense? Everybody follow? Speak now. All right, we can move on. Okay. So the benefits of steam flaking is not just about how it impacts that pericarp and exposes the endosperm, okay? It also causes what's called starch gelatinization, okay? So pulled most of this from Richard Zinn's paper out of 2002. In typical yellow dent corn, okay, those granules, that endosperm is about 27% amylose, okay, and 73% amylopectin, okay? So amylose is glucose molecules bound together in a straight chain by alpha-1,4 linkages, okay? Amylopectin still has that amylose branch or straight line, but it also has these branching points, which are alpha-1,6 glucosidic linked chains, okay? So amylose is going to look like a straight line of glucose. Amylopectin is going to look like a bush, right? Where you have some straight lines, but there's going to be branching off at those alpha-1,6 glucosidic bonds, okay? All right. So the starch granule, because a bulk of it is that amylopectin, and it's going to have this bush-like effect, okay? That starch in corn is going to be crystalline, okay? So this is that starch, these are starch granules from corn viewed under electron microscope, okay? So you can see how crystalline these balls of starch are, okay? So panel A is unprocessed grain. Panel B is following steam application, okay? When we apply that steam application, those crystals, in essence, melt, okay? Makes it to where those microbes can access and utilize that starch granule, that amylopectin, better. Does that make sense? Any questions? Okay. Unprocessed corn grain. So if we just took corn, ran it through a dry roller, made dry rolled corn, okay, didn't expose it to a large amount of heat and steam, that starch granule is going to be very crystalline in structure. When we steam flake it, and we add heat and steam, water, it's going to melt that crystalline structure and basically get rid of that crystalline structure in the amylopectin. Does that make sense? Do you follow? Okay. All right, so with heat, starch becomes gelatinized, okay? The way this gelatinization is an irreversible swelling of that crystalline starch structure, okay? So we can't really measure or we can't really define gelatinization. So the way we define it is by how we can measure it, okay? So it has a loss of this birefringence, okay? When we observe it through electron microscopy. So birefringence has to do with the reflective characteristics of these granules, okay? You have clear granules displayed here in the unheated grain. However, those disappear in the heated grain, okay? We can measure swelling power, we can measure solubility, and then we can measure enzymatic activity or reactivity. So we can measure starch availability by incubating it with amylase and then measuring glucose production. So how much glucose gets yielded from a given amount of amylase or amylose when we provide or mix it with amylase. Okay? Any questions on this? Okay. So this is just a diagram. These straight lines are amylose. Okay. See these straight little squiggly lines? So those are glucose residues bound together by just alpha-1,4 linkages in a straight line. Okay. This thing that looks like an upside down tree branch is amylopectin. Okay. So within the amylopectin, you can see these branches that are straight line, and those are bound together by alpha-1,4 beta linkages. But these where it branches away from other straight lines, that is alpha 1,6 glucosidic bonds, linkages. Okay? So envision it as amylopectin looking like a branch, amylose being basically just a straight line of glucose. Okay? Any questions on that? Amylose is a lot more available to ruminal microbes than amylopectin. Okay? So if we add temperature and water and cause that gelatinization process, you can see how that bush swells. And it exposes more of those uh, glucose chains within that amylopectin to microbial fermentation. Okay? Doesn't necessarily do much to amylose, but it makes that swelling of amylopectin greater. Okay? If that steam flake corn, as it starts to cool, it'll form that gel ball. Okay? And so that swelling will kind of decrease a little bit. These amylose lines will form these squiggles. Okay, still very available to the rumen microbes. Even though it's a little less swollen, this amylopectin is still more available to the ruminal microbes. However, over time, if we allow that steam flake corn to sit, time and some heat, so let's say like you have a stack of steam flake corn, the center of that stack could have some heat production, okay? That can cause retrogradation, so it won't be exactly the same as it was prior to steam flaking, but it's going to reduce starch availability to some degree, okay? So that's why a lot of feed yards will feed steam flake corn that is produced that morning or that day, okay? Let's see. Oh, I don't remember. Trotta, this paper here, looked at it, and I think they did it for looked at it over a week. Okay. So, in bushland and other research feedlots, they're feeding steam flake corn. That's great because it is uh, uh, more indicative of what their stakeholders in their local region are doing, right? But do you think we had a steam flaker? Do you think we were steam flaking our own corn? Do you think that we were buying a fresh batch of steam flake corn every day? No, that corn's going to be delivered. We went through about a truckload a week, okay? But at the end of that truckload, it would have been sitting there in a pile for a week. So we probably had some measure of this retrogradation happening, okay? Yep. Yeah, so Trotta did this. He looked at storing steam flake corn at 73, some more ambient temperatures versus 130. So in the center of a stored stack, it could get that hot, okay? And then found that starch availability decreased by about 50% to 60%, depending on the storage length and conditions. Now, you can look at that paper and figure out what exactly those conditions were that they were exploring. I don't remember. But good question. So kind of an appreciable amount. Still likely better than dry rolled corn, but real old steam flake corn is not going to be the same as fresh steam flake corn. Okay. So yeah, this decrease in starch availability reduced ruminal starch degradation by 20%. Okay. So this starch availability was just measured using an enzymatic lab-based procedure. Okay. So that's why it's 50 to 60% here in the lab, but it only reduced starch availability by 20%. Still appreciable, but not as big. Okay. All right. Any questions about grains? We're good? Okay, moving on. Corn milling byproducts, or really we should call them co-products. A paper I just looked at the other day showed that about 22% of an ethanol plant's revenue comes from selling distillers grains. Okay, so a more byproduct would be something that's produced and is like a waste product or they're looking to get rid of it. But this distillers grains and these other products that are coming from ethanol production or corn syrup production, they're very valuable to those factories, okay, as feeds for cattle. So, distillers grains are byproducts of ethanol production. They have, each plant has a different procedure, okay? And there's variation in the feed stock that they're putting into the ethanol product system. There's variation in the quality of those grains, okay? But you see a huge amount of variation from factory to factory in terms of nutritive characteristics of distillers grains, okay? So we can feed distillers grains as wet, okay? So they take it out of that ethanol plant, put it toward no or very minimal drying. And so it's going to have a very high moisture content, okay? They can deliver that from the ethanol plant directly into a feed yard, but that feed yard needs to feed it relatively quickly, okay? Also, they have to be located kind of close to these ethanol plants. Otherwise, you're paying to ship a lot of water, right? Does that all make sense? Okay. So there are modified distillers grains. So that's kind of an intermediate drying between wet distillers grains and dried distillers grains. So maybe feedlots that are a little farther to where it doesn't make sense to use wet distillers grains from the ethanol plant, maybe they'll feed modified distillers, okay? And then there's true dried distillers grains where they dry them to, I know I have a slide here that has dry matter percent, so I don't want to quote myself wrong, okay? Then we also have byproducts of corn syrup production, okay? So we call these corn gluten feeds. Corn doesn't actually have gluten, so it's a misnomer where we call it incorrectly, right? Only wheat really has gluten, isn't that right? Okay. But it is the pericarp and that cap tip from the corn grain. So this could be dried, it could be wet. The big product, a lot of feedlots are feeding this, is from Cargill Animal Feeds, Cargill Animal Nutrition. Cargill branded feeds is actually what it's called. Okay. Branch of Cargill. So they have Sweet Bran. Okay. So that is a wet corn gluten feed. They have Ramp. Okay. Wet corn gluten feed mixed with some alfalfa hay that's supposed to be directly fed to receiving cattle. Anybody say something? No? Okay. So it's supposed to be a complete starter / grower ration. So you buy this Ramp and feed it directly to your receiving cattle. Okay. Then they also have One Track, which is a wet corn gluten feed product for dairy cows. And it's supposed to have a vitamin and mineral pack in it. Okay. So we actually did a study with lactating dairy cows in bushland. Those poor interns from Brazil were milking these cows twice a day for 150 days. We had about 40 cows getting milked in a feedlot. It's a bit of a train wreck, okay? But it, in essence, replaced about 6 ingredients out of our control ration, okay? Yep.
Obviously, right, the straight from where it's made to wherever the production is. For the modified and dried, is it staying where it's made and then getting shipped out after it's been dried, or is it getting shipped out, dried at that place? Like, how does that work?
I'm gonna guess that plant will dry it there at the same factory that they're distilling ethanol. Maybe they have another place where they take wet distillers grains to dry it. I don't actually know. But it would arrive to the feedlot, yeah, dried to whatever extent you're buying. Okay. Okay. Picture of Sweet Bran, picture of wet distillers grains, picture of dried distillers grains. I had to put alternative captions on these before I upload them to Canvas. Otherwise, I get a meter that says it's not accessible. It'll be in the red. But it looked at this picture. PowerPoint will automatically try to do that. It looked at this picture and said sand. So I thought that was funny. Dried distillers grains, wet distillers grains. Okay. All right. Here's the NASM tabular value of dry, modified, and wet corn distillers grains. You can also have distillers grains produced from sorghum. Okay. So dry distillers grain is going to be about 90% dry. Modified was about 48%, and then wet is 31%. So wet distillers grains will have about 70% water. Okay. Crude protein. The process of drying crude protein isn't really going to change the amount of nitrogen that's in feed, so we wouldn't expect the process of drying distillers grains isn't going to change the amount of nitrogen in that feed, so we wouldn't expect that to change much or at all, and that's kind of what we saw. RDP, 30% RDP for wet, 32% for dry. I'm going to show another slide here where we actually measured RDP experimentally when I was with the USDA of wet and dry distillers grains, and it is a much more drastic than what the tabular values from NASM will say. Okay. Drying is not going to change ether extract. Okay. Remember these tabular values were published in 2016. So 10 years later. So I'm going to show you some more modern data of dried and wet distillers grains that it will look very different. Okay. NEM, so you see a little reduction in energy value of these feeds as it gets dried. Okay. So that's going to be caused by that Maillard reaction from the process of adding heat to dry out the water. Okay. So NEM, TDN, NEG all follow the same pattern. And then again, you wouldn't expect any change in fiber content. Okay. Okay. So based off the NASM tabular values, wet distillers grains has about 104 to 116% of the energy value of steam flaked and dry rolled corn. Okay. So there you can see NEM for steam flake corn, they have it at 108. For wet distillers, they have it at 112. I don't believe that. I think typically it's about 95% of the energy value of steam flake corn. Okay. However, what was I going to say? Lost my train of thought. Okay. But the difference in this energy is really coming from ether extract. So we'll show you this data I'm promising that is from distillers grains that were collected at bushland at different plants around the high plains. That ether extract has decreased in especially dried distillers grains. Okay. They're pulling more fat from these distillers grains to support biodiesel production. Okay. So that's going to change the energy content of dried distillers grains tremendously. Okay. Cool. All right, here's that data. This was published by a student did his research out there at Bushland. So those previous tables were from NASM. However, this was from, we did this work in like 2021 or 2. Starting to get to where I can't remember. Okay, so we looked at a bunch of different protein feeds, but let's just focus on wet and dried distillers grains here. Okay, again, the drying process, we wouldn't expect it to change crude protein content by very much. However, dried distillers grains that we were buying at Bushland was 4% ether extract compared to the NASM tabular values, which were almost 11%. So they're pulling out an appreciable amount of fat today. Wet distillers grains were still really high at 11%. Okay, the TDN value of wet distillers grains was 93.5. For dry distillers grains was 92. Okay, so that change in TDN was being largely driven by that dry distillers grains having less fat. Okay. So we saw a 93.5 TDN for wet distillers grains, 82.3 for dry distillers grains. compared to the tabular values of 98 and 89. Okay. So why is wet distillers grains higher in energy than dried distillers grains? Beyond just the fat content of those distillers grains, it's largely driven by, so TDN is directly related to organic matter digestibility. Okay. So how much of that organic matter in that feed is available for that animal to use? Okay. So if we assume that all other processes to arrive at wet distiller's grain is the same, and the only thing we're changing is then that wet distiller's grain gets dried to arrive at your dried distiller's grains, it is likely because of heating the dry the dried distiller's grain will form Schiff bases or Amadori products. So these are the products that are occurring through the Maillard reaction. Okay. This Schiff base is really reversible. So if it only gets to here, you can have an appreciable amount of it go back to this dex or D. What is the D? There's levorotatory and dextrorotatory. So D-glucose. So an appreciable amount can go back to there. Again, it takes a glucose residue, so it could be cellulose, could be some other sugar molecule, and then it takes some source of nitrogen, so protein, to bind to that to make these products. Okay. If it stops at the Schiff base, it's really reversible. However, if it carries back all the way to this Amadori product, it's much less reversible. So this is much more indigestible than Schiff base, which is much more indigestible than this dextroglucose. What is it? Levorotatory, dextrorotatory. Who remembers what those are? Isomers of each other. So it has to do with, so think about like hands. So these are kind of copies of each other. They're mirror images of each other. However, they're not the same, right? My thumb's on the other side or whatever. That's how I think about it. Not very scientific. Yeah, but if you think, let's just imagine my fingers are glucose molecules or whatever. Okay. Let's pretend my left hand is L, my right hand is D. Okay. They're mirror images of each other. However, they're not the same. And so they'll have some different properties. Yep. Yeah, it'd be true protein contained within the feed. Same thing happens with crust in bread. It is the starch binding to amino acids or true proteins, peptides, or whatever else in that flour. Okay. So it's much more reversible if you have the Schiff base. That's why those arrows are the same length, right? However, Amadori, some of it could be reversed. However, there's more being produced than can be converted. That makes sense? That's why that arrow is shorter compared to the other one. Other questions? Okay. All right, so wet distiller's grains appears to be the winner on a nutritive characteristic basis. Okay. Especially today where they're extracting more fat from dried distiller's grains than from wet distiller's grains. Okay. So what are some disadvantages to wet distiller's grains that you guys could think of? Why would it be more expensive? So you're paying for a lot more water. Okay. So logistics wise and transportation costs, it would only make sense if you're pretty well localized, co-localized with the factory. Yeah. Spoils real fast. So you get a load in, you probably need to feed it within at least a couple of days. Okay. Messy. Yeah. Yep. It cakes up real bad. So if you think about a feed guy that's driving the payloader, has a bucket on the front of it, takes a big scoop. He's loading the mixer wagon. All of a sudden, a 300-pound clump falls in. You've now overloaded wet distillers grains by 200 pounds, right? So that's a big issue, especially if that operator of the payloader is not getting out and pulling it out, or if he's lifting up on the feed truck and making the scale say 0 and showing on paper that he actually loaded correctly, basically giving away 200 pounds of distillers grains for free. That's a big issue that happens a lot. Okay. Cool. All right. Spoilage. Okay. High moisture ingredients need to be fed quickly. So large feed yards will receive loads of these ingredients very frequently, multiple times a week. Oftentimes, I know they did at Wrangler, they'll actually store it in silage bags so that if some weather event happens or something happens at the plant, they have a little bit of buffer to where they can hedge their bets against acts of God where they couldn't get a load in, right? Okay. You need to be located near an ethanol plant. You have increased shrink. Okay. Whenever I talk about ingredient shrink, that is losses of ingredients that you paid for that you won't be able to capture or bill out to your consumer or your client, right? So as that you paid for that wet ingredient, as it dries out, you have lost an appreciable amount of inventory. Okay. And then increasing wet distillers grains in the diet will reduce dry matter content of that diet. I think that should be pretty obvious. And increase the number of loads needed to feed. So I took this example directly from Dr. Steve Armbruster, who came and gave a lecture to me whenever I took stocker and feedlot management at Oklahoma State. So that's kind of cool. Dr. Armbruster was one of the initial people. Him and Kenneth Ing were one of the first consulting nutritionists. And at one point in time, he had about 1.5 million head on feed. He came and talked in a lab. We spent 3 hours with him. Probably would have been worth about, I don't know, $20,000. Okay. So one scenario, we have a 1 million pound ration that we're feeding daily. This ration is 73% dry matter. Okay. So if we have a 24,000 pound load capacity truck to feed our 1 million pounds of ration, we would need 1.37 million pounds as fed. So capacity of the truck's 24,000, so that'd take 57 loads daily to deliver all the feed to the cattle at our feedlot. Okay? So that can be done in about 9 hours. Okay? Compared to a diet where we increase wet distillers grains, so we're increasing the amount of a wet ingredient. Now our dry matter percent is 65%. Okay? Now we have to deliver 1.54 million pounds as fed. We didn't change how much dry matter of feed we're delivering, but because it's wetter, we have to deliver more feed on an as fed basis. So now it's going to take 7 more loads a day, so 64 loads, and it's going to add a little over an hour each day to feed all those animals. Okay? Make sense? So potential big issue. Okay? All right, things to consider when feeding high corn milling byproducts. So if you're feeding a diet that is very high in distillers grains, for example, so this says 40%, I can tell you that's what Wrangler Feedlot is doing. They have about 50% steam flake corn, 40% wet distillers grains. Okay, so this is not that far off of what some feedlots are doing. So if we include high levels of byproducts, it's going to increase crude protein content tremendously. So in this example diet, our crude protein content is 17%. Okay, cattle, we can meet our cattle's crude protein requirements in a finishing setting at about 12%. So we're way oversupplying crude protein relative to their needs. So that excess nitrogen they're consuming will be lost, excreted through urine. Okay, as soon as that urine hits, and predominantly through urea in urine, as soon as that urine hits the manure pack on the pen surface, It's going to be introduced into ureases. That urea is going to be converted to ammonia, which will be volatilized. So about 70% of nitrogen consumed by feedlot cattle is lost from the pen surface through volatilized ammonia. Okay. Okay. Then some of it will also be lost as nitrous oxide. Okay. Another big issue, phosphorus content. These ingredients are typically going to be very low in calcium, very high in phosphorus. So if we don't add an absolute boatload of limestone, this diet has just under 2% limestone, then we wouldn't have an adequate calcium to phosphorus ratio. Okay? So another thing to keep in mind. Additionally, this excess phosphorus, like with urine, will be excreted. Okay? Or urine nitrogen. It's going to be excreted in urine. Some of it's going to be excreted in feces. Now that phosphorus isn't going to volatilize like nitrogen did with ammonia. However, it'll get leached out into waterways, cause eutrophication, environmental pollution, etc. Okay? So 2 issues. Okay, another issue, sulfur content. Corn milling byproduct feeds classically have a lot of sulfur. Okay. Distillers grains, according to NASM, is 0.66% of sulfur on a dry matter basis. Okay. This sulfur is being brought into that ingredient because they're using sulfuric acid to stop the fermentation process after they've generated their ethanol. So I will say modern distillers is likely much lower than this. However, it's still going to be very high. So this example, we have 40% distillers grains. Our sulfur content is 0.34. Okay. The safe limit, the rule of thumb, is 0.4%. Okay. You start getting above that, you can start running into issues. So one of these issues is sulfur-induced polioencephalomalacia, PEM. Okay. Who's ever seen an animal with PEM? So they call them brainers, but they'll display neurological issues. So they'll be unresponsive to contact, like even if you touch their eye, they're going to be unresponsive. Okay, I think maybe Thursday I have some slides on this some more, but just to kind of set the stage, PEM from sulfur-induced PEM has been suggested to arise 2 ways. Okay, the first, excess sulfur goes to the rumen. Rumen microbes convert that to H2S, so hydrogen disulfide or dihydrogen sulfide. Hydrogen sulfide. It's called hydrogen sulfide. Okay, so this H2S is a neurotoxin. Okay, you hear about it about once a year. There will be a case of a guy working in a swine barn, and the manure in that swine barn will produce H2S, and then these people will die because of H2S poisoning. Okay, they'll pass out. They'll exhibit these atypical behaviors, pass out in there and suffocate and die. Okay. So H2S overrides mitochondrial sulfide oxidation at the cytochrome C oxidase level. You don't need to know that. I don't even really know what that means. I know the cytochrome C oxidase is involved in electron transport in mitochondria. Okay. So this results in decreased ATP production, leading to decreased energy reaching the brain. Predominantly, glucose is the main energy currency for brains. So it's produced in rumen, eructated, so belched out, and then they'll breathe it back in and experience this H2S toxicity. Okay? So the other suggested means is a sulfur-induced thiamine deficiency. Okay? So I'm pretty sure I have another slide on this, so I won't talk about it too much. But the treatment is you give them a shot of thiamine. So if you want to feel like the man or the woman, and you want to feel like you're just God's gift to curing animals. Go up to an animal with PEM, give them a shot of thiamine, and it's almost instant how they'll recover. Okay. Any questions on byproducts? Okay. Moving on to roughages. Roughage ingredients will have high fiber content. Surprise? No? Okay. They can be forage based, so silages, hays. They can also be byproduct based, like cord or cotton burrs, which is like the rebrand of the century. Whenever I was in college, they called that cotton gin trash, but Cotton Inc. rebranded that to cotton burrs because it sounds better. Okay. Crop residues, so corn or sorghum stalks, wheat straw, etc. Okay. Soybean hulls, another example. Needed in the ration to add scratch factor, okay, and a level of safety, okay. We do not include these in a finishing diet to bring in energy or protein or any appreciable minerals. All we're really trying to do is add physically effective NDF. Who remembers what that is? What? Yeah, but what is the physically effective neutral detergent fiber? So it's a measure of how much chewing activity that animal's going to have. Okay? All right. Physically effective NDF is going to stimulate chewing. This chewing will buffer the rumen through saliva production. Okay? This is predominantly through salivary bicarbonate. Okay? Cattle will swallow about 140 milliliters of saliva per minute. That ends up being a lot. While they're eating, and about 95 milliliters per minute while resting. Okay? So that amounts to about 180 liters of saliva per day. So you can divide that by 4, and I'll tell you how many gallons that is. Okay? So that'll provide about 25,000 milliequivalents of bicarbonate and what is HPO4? Phosphate buffer? I don't know. Okay. So here's this study where I pulled all that information from. They looked at feeding, so this is physically effective NDF at an 8 millimeter screen size. So they take the ration, they put it in a Penn State particle size separator. Know you guys saw this in Feeds and Feeding. They'll shake that, turn it, shake it, then they'll measure particle size and what percent of the diet accumulates on each screen. So as it goes from big holes at the top to smaller holes to a pan at the bottom. Okay, so this is physically effective NDF at the 8 millimeter screen. This is physically effective NDF at the 1.18 millimeter screen. So they had a high forage diet versus a low forage diet. So you can see that physically effective fiber, independent of what screen you're looking at, decreases in the the low forage diet. Okay, so impacts on pH. So the amount of hours per day where ruminal pH was below 5.8, huge increase. So the high forage diet only spent 3/4 of an hour a day below 5.8. The low forage diet was about 6 hours a day below a ruminal pH of 5.8. Okay. Same story with time spent below 5.5. Okay. Salivation rate. So high forage diet increased salivation rate in milliliters per minute. I don't exactly know what insalivation of feed is, but I guess it's milliliters of saliva produced per gram of dry matter intake consumed. Okay. And then this is resting salivation rate, milliliters per minute. So it also reduced that. So more fiber, more forage, increased chewing stimulates saliva production. Saliva production provides buffers through bicarbonate predominantly to impact ruminal pH. Make sense? Okay. Here's a picture of the Penn State particle size separator. So different screen sizes from the biggest to the smallest, and then a pan to catch the small particles. And so you measure the percent of diet. In the US, we use the 4 millimeter screen as our base for measuring PE NDF. Then you figure out what percent of the diet is 4 millimeters or more, and then you multiply that percent by the NDF content to get PE NDF. So it's a measure of chewing activity. So if you feed more PE NDF, cattle should chew more and produce more salivary buffers. Okay. We have 1 minute. Maybe I'll finish this later. Okay. Any questions, guys? Cool. Do your exam corrections and bring them to my office or Kyle's office. If I'm not there, slide under my door. But staple your corrections to the top of your exam so I can see which ones you missed and match it up with which ones you re-answered. I'll re-hand them back out.
We should not like fix them on the original one, but we should